Talking. So the Navier-Stokes equations govern fluid dynamics. Fluids is not just like liquids; it's also gases and plasmas, anything that flows or can move. And they have equations to model it. It's called the Navier-Stokes equations. And the most common ones to reference are continuity and momentum. Conservation of momentum is the flow related one, and it's the one I did the video on. And we're going to go over parts of the video, but I did want to point out some other values. Like I want to say Lawrence asked me about this the other day. Does temperature come into it? Well, we've got the energy equation. If we're looking at how energy is affected, and it's not just the constant energy or constant heat throughout. So like Q is represented by heat flux, changes in heat. So it would make sense to think that temperature shows up somewhere in this equation. And we have the Reynolds number and the Prandtl number. If we look at the Prandtl number, you will find that it has thermal diffusivity in there. So it does measure the conservation of energy equation measures or keeps track of the thermal energy as well. In terms of the way that the momentum equations goes, they often write it as du dt with a big D. I'm writing really big. I think that pin's dead. There we go. Come on. Du dt. And that's a shorthand notation they use to cover little d, du dt, plus we've got u dotted with the gradient, and that's applied to u. Okay. So this is changes in velocity with over time. And that one's over time. And these are spatial changes. Okay. That's a plus. This is a little funny to look at. If we've got u, let's say u, the u function is ubw. Then what this term is really saying is we've got ubw dotted with the gradient operator. A dot product yields a scalar. And then we're multiplying that by u. And it looks weird. Because we've got u d dx. It's not a vector anymore. And we're applying that to UVW. And that hits each component. So the I component is u du dx plus v du dy plus w du dz. The j component is u dv dx plus v dv dy plus W dV dz. So the I component represents conservation. This is part of the momentum equation. This is changes in spatial velocity changes. And this one is in the X direction. So it's affecting conservation of momentum in X. Which is kind of crazy because we've got V and W in there. We know V is the Y component of velocity. W is the Z component of velocity. So it's kind of like, how does this affect what's going on with the X component of momentum? What's going on? So when you're when you're working with it, it's a lot to unpack. And computers are usually the way to go through it. The right-hand side of the equation isn't any nicer. So the right-hand side of the equation has, we've got, remember, this is conservation in momentum, of momentum. And the right-hand side is, it's affected by pressure differentials. So if there's a change in, if there's a pressure gradient, it's low pressure on one side, high pressure on the other. Like picture a pipe, flow in a pipe, water in a pipe. If there's high pressure on one side, low pressure on the other side, the high pressure is going to cause a flow towards the low pressure area, try to balance out pressure. So it does affect momentum. We also have external forces. External forces are like the effects of gravity or something like that. So this is a pressure differential. These are external forces. Gravity is just one. And then we have stuff that's related to viscosity, or how much is converted to deforming the object. And that is mu times the Laplacian of the flow field. There's the viscosity coefficient, mu. This is for dynamic viscosity. Which is changes by motion. Changes by motion. And viscosity is like thickness, kind of. So this term is measuring how much the object resists change. Like the particle or whatever we're looking at. Resists change. What happened? I think someone came and left. What is going on? changes from shear flow. So we got some particle and water's flowing towards it, or there's flow around it. The flow's hitting it. Is the flow causing it to generate waves? The surface? So when it's shear, it's like shear is, how is it affecting the edges? From the side. So shear flow is like going across the top or the bottom here. Other types of flow, like if the water's pushing directly towards it, it's called something different. That's that something pushing directly towards it is not shear. So it's like, how am I, like if you got a water balloon and you blowing water or air at it, does it change the shape of the water balloon? Because it's hitting the sides, and does it bend it or anything? So there's a lot of shit they track. Because this U is, again, the U, V, and W. And when you take the plotting of it, you get stuff that's affecting, well, how's it affecting side A, side B, side C, sides underneath? There's 6 different sides we could have where it's affecting it. How's it affecting each side? So that ends up often being, depending on how they set up the system, a tensor or a matrix. Sometimes they do it in cylindrical coordinates, like I would use here with the square. If you're looking at a water droplet, you might be using spherical, stuff like that. So there's a lot going on, and since there's so many different things that change, they want to really, like, how can I reduce all the different variables? Let's gather them all up, figure out something, what's going on from there. And that's where the non-dimensionalization comes in. Can actually make the problem a little bit easy to follow. And it's as simple as, let's look at the du dt again.
You have to bring the board down. Yeah.
So what they do, non-dimensionalization, non-dimension, no dimension. That's what non-dimensionalization means, no dimension. Let's get the dimensions out of it. No dimensions. Let's get rid of them. Now I have a time in here. I've got T in here for time. U is flow or velocity. And the gradient is related to 1 over distance. Because it's ddx, ddy, ddz. That's our gradient. This is like X, Y, and Z are all measures of length. And they're all on the bottom here. So it's kind of like a 1/distance kind of thing. It's measuring small distance changes. So what we do is we start with the equations. Let's just, I was using asterisks. So I'll go back to doing that and maybe put a little dot there. So what I want is my U to end up without dimensions. So I've got U, I started with U dot. If I want no dimensions, I need to divide out dimensions. So let's come out, like, I don't know, the problem is I don't know what the dimensions are in U. I do know it's distance over time. Velocity is distance over time. And I could break that up into distance and time here. But everything in this conservation of momentum equation has a U in it. So rather than shift it all into distance and time, I'm going to use U as, I'm going to use velocity as a dimension. It's just going to have more than one component kind of thing. So we'll go with V as a dimension. If I could, let's see, can I make a good U? I don't know, that looks funny. I'm going to go with V is my units of dimension. So if V is my units of dimension, let's say it's miles per hour or kilometers per second. I don't know what they are. I just want to get rid of them. I'm going to divide by V. This leaves U without dimensions. Now it's just a value and a direction, a magnitude and direction, and we're not assigning any scale to it. I could be going, you know, kilometers per, like I said, second, miles per hour, light years per minute. I don't know, warp drive, Star Trek. Again, it's the point is that it doesn't have the units anymore. So I want to do that with all of them. If I do that with the gradient, I've got gradient star. And I was saying it was a measure of distance. Let's call distance L. And I said it's 1/distance, so I'm going to divide by 1/distance. And I've got T to work with. If I take this equation right here and solve for T, multiply T to the other side and divide by V, I get T equals L over V. So I'm going to say T equals T star divided by L over V. And that's a little ugly, so I'm going to multiply top and bottom by V over L. And I get, this is T star times V over L. Pause for a second, let that soak in. If I do that here, I'm going to get multiply top and bottom by L. I get gradient equals L times the special one, the original. Okay, so we had our initial equation had all the asterisk versions. So like maybe I should solve these for the asterisk versions. So if I solve this for the asterisk version, I'm going to get U star equals V times U. Just multiplying through by V. When I'm looking at these two, if I want to get gradient star by itself, I need to divide both sides by L. I get that's the gradient over L. And if I want to get T star by itself, I kind of need to multiply both sides by L over V. Okay, so let's non-dimensionalize the left side of this equation. I'm going to rewrite the equation. I'm going to rewrite our little values that we had. We're looking at du dt star star plus u star dotted with gradient star.
Would you move the board down a little bit?
Yep. And times u star. And recall u star was VU. That looks funny. Big V, little u. And T star was LT over V. And we had gradient star was gradient over L. So I'm going to make those substitutions. So at this point, like V and L are units of measurement. They're not, there's no changing them. They're not affected by derivatives. So this becomes V over L over V times du dt. Plus, I just pulled them out. Here I'm going to pull out, this V will come out there. That L comes out, goes on the bottom. And this V is on the top. And I've got my U dot gradient U.
So as I understand it, you essentially made it so that the partial was not the stuff that you non-dimensionalized, you made it so that they're not dependent on the partial derivative.
Say that again. These are not values, they don't change.
They don't change, yeah.
They're constants.
Mhm.
So they're not affected by derivatives.
Yeah, that's
Constants
what that's what I was saying. You
That's
made
what-
it
okay.
so that
Yeah.
they're not dependent on the partial.
Yeah. And that's why I pulled them out. If I rewrite this one, if I multiply this by V over L on top and bottom, you're going to see I get this whole thing turns into V squared over L also.
That looks like a acceleration.
Kind of, doesn't it? You've got velocity squared. The only other component that's in the left-hand side of the equation is not just du dt. This is all multiplied by density. So the original equation has rho du dt plus u dot the gradient u. And so if I put that in here, I was just looking at, this does not, we're not going to change out the units. We're going to leave density alone. Leave that shit alone. It's already just units. It's not a vector, so we don't need to worry about changing it. And there's no derivatives hitting it or anything like that. We're going to leave it alone. So if I put all this shit together, I've got, and I factor out the V squared over L from both of these terms. I've got rho V squared over L times du dt plus u dot, not plus, u dot gradient u. And that's the left-hand side of the Navier-Stokes equations. Now we're going to want to divide by this later on, but we need to work on the right-hand side too. The right-hand side of the equation, the base setup, again, is the negative pressure gradient plus external forces. Let's just say it's gravity for now. It's affected by density. And we've got those viscous forces that are acting on our particle. Most of these we've already seen the parameters for. We've dealt with mu, we've dealt with this, the Laplacian is del dot del. So the del, if I do that in terms of the original, that's del star over L times del star over L. And you end up having like a 1 over L squared for the Laplacian. G, we're just gonna, let's just say G has units G, big G. So we're gonna say G equals G star divided by big G. Because we don't know if we're doing meters per second squared, you know, if we're doing SI or our good old feet. We don't know what they are, so we're just gonna leave it as G. And so that leaves us with P. P doesn't have any good units to work with, so this is what they've done. They said, all right, so if the flow is dominating, if it's fast, if the flow is fast, if U is much, much greater than 0, so like fast, then things that are affected by speed have the biggest impact. Viscosity is kind of like meh. This fast flow affects it the most, and so they define P to be P star, and we divide out density over velocity squared. So when we solve P star, we got P star equals rho V squared P. For low U, viscous forces dominate. And then they say, just jump into the chase, P star is mu over V times L with P. But let's face it, low velocities is not very exciting. Many of these tests were done, they did things experimentally. So they would, in fact, Ames Research Center, when you visit there, I'm going to try, if they are open, if NASA Ames in Mountain View is open to tours in spring, I'm going to try to arrange and pay for Mesa to go, or at least a busload of Mesa students to go. I was in contact with him at my contact over at NASA Ames at the beginning of fall. They were still in like not accepting visitors mode from the pandemic. Maybe it's changed. I hope it's changed. I'd like to take you guys on a tour there. They have a giant, it's like effectively like a giant long fish tank, where there's the water, it just keeps flowing from one side to the other. So the water goes through this fish tank, goes to the other side and gets recycled around. And they introduce so it's like a fish tank. And there's water flowing through it.
You have to bring it a little
Oh, we
down.
can't see the bottom.
Okay. Yeah, sorry. The water's flowing through it straight through so that there's no eddies or anything like that. And what they do is they put a little tiny needle that sticks in that just slowly oozes dye. So the water's clear and the dye shows up. You can easily see the dye. And when the flow is low, nothing happens. The dye just kind of goes slowly down. It might spread a little bit. And that's for low U. As soon as you kick that U up into high gear, when U goes, so they have a little flow like turn dial. When U gets large, you start seeing a lot of turbulence. The dye goes crazy. So a lot of the stuff that we're using this for, we care when stuff is causing turbulence. So we're going to focus on this one right here. That was all to go with, like, to lead the argument for using this one. I hope that they're open.
So
Yeah, that'd be awesome. I'd love to go.
Yeah, I figured most of you would. Go ahead, Brandon.
yeah. So for anybody who's planning on taking differential equations or even the modern physics class for that matter, this is from what I can tell, this is definitely differential equations. Like looking at the right hand side, or sorry, the left hand side that you had, that one, that's a differential equation that if you have the
To
value,
solve it, yes.
yeah, you can solve that.
Well, I mean, you can. We have computers do it because it's not simple by hand, especially when you have the right hand side as well.
Yeah. But
Uh,
for anybody who's interested, this would probably be what modern physics has to offer.
I don't know that modern physics touched on this.
Okay. Well, stuff like this, I'm sure.
Uh,
I can't.
this
tell
was
the physics.
this was stuff I did in grad school. I
Oh,
know
really?
that undergrads can do it at UC Santa Cruz because the class on fluid dynamics was for both grad students and undergrads. He just gave different homework sets to depending on whether you were a grad student or not.
Okay.
Grad students actually had real homework, and undergrads were it was a lot more trivial homework assignments. But like this affects a lot of things. Like I'm just showing water going down like a fish tank here, but we're talking about things that flow like air. So this is like kind of affects like turbulence over an airplane wing. Because we're moving the object through it fast, the wind's blowing faster. That's what causes turbulence. This stuff has a lot of impact in like real world applications. It's just really fucking math intensive physics. So let's take a look at plugging all this shit in here for this right hand side. So let me rewrite the right hand side. We've got the negative gradient. I'm off screen still. Negative gradient P. And we got rho G. And we've got mu Laplacian squared U. And U star is the U, big V, little u. My G star is going to be big G, little g. Laplacian is 1 over L squared, or Laplacian squared over L squared. And for P, we're using P star is rho V squared. P. Oh, gradients in there. We already did the gradient. Gradient is 1 over L. So gradient star is gradient over L. So let's stick these in. I've got negative. These are all the starred versions. So let me maybe put a star on real quick, or a dot next to them. So this becomes gradient over L. And this is rho V squared P. If I do my external forces term, in this case, I went with gravity, but that's not always just gravity. Rho GG. And here I've got my viscosity term. This is a del squared over L squared VU. So cleaning this up a little bit, if I put this rho V squared over L in front, I've got negative gradient of P plus rho G over, not over G, times our gravity vector, plus I put all the units or the scalars out front. That's where we're at right now. Okay, so this is the right-hand side. This looks familiar. This is what we have on the left-hand side. So I kind of, if I want to clear it out, I need to get this to appear in these also. I want this on all of them. So how can I go about making that happen? I'm going to start, let's look at the gravity term. I've got rho G times G. And I want to end up with a rho V squared over L. Somewhere in there. I don't think, it looks like the G is going to have to stay by itself. Which means I could multiply. I'm going to have something else in here with this right here. I have the rho already. What I'm missing is the V squared over L. So I need to multiply this by a V squared over L. And so to keep things consistent and not like change the value, I'm going to multiply by the reciprocal. So we're going to put that in here. And we're going to look at doing the same thing with the viscosity term. We've got mu V over L squared gradient or the Laplacian of U. And I want to end up with a rho V squared over L. And I'm going to have a gradient of U in there, or a Laplacian of U in there when I'm done. What's got to happen here? It looks like if I want to end up, I'm missing a row, so I need to add in a row. And I'm missing a V. So I need to add in a V. And I actually have one too many L's on bottom, don't I? If I just don't want a single L and I got L squared, to address that, I can multiply by L too. If I do that, I will have the rho, the V squared, and the L. So that part's met. I need to put in a 1 over rho VL to offset it, so that I'm not changing the value. Which means this part is going to go in with the mu. I got mu over rho VL. So we're almost done. If I rewrite this whole equation now, I've got rho V squared over L times the negative gradient of P plus G over L V squared G plus mu over rho V L and the Laplacian. That's my right-hand side. So now rho V squared over L is on both sides. We can clear them out. They're just units. And the only spots units show up now on the left-hand side or the right-hand side is here and here. We've got them all wrapped up in two spots. The Reynolds number is rho VL over mu, which makes that term 1 over Reynolds number Laplacian of u. For some reason, they would like to use a squared term for this other one. It's also upside down. So if I do V over the square root of GL, this is called Freud's number or Froude's number, F-R-O-U-D-E. This is Reynolds, like Ryan Reynolds, but not Ryan Reynolds. And that makes this 1 over Froude squared, G. So now they've got all the stuff, all the things that change tied up in two spots, and they can see how different unit systems and stuff affect things. And so when they're plugging this stuff in the computer, I mean, for any given scenario, any given units, they solve the system of equations just like Brandon was saying. You're doing differential equations. You've got a bunch of equations, a bunch of unknowns. It's much easier for a computer to solve this. And then they go, okay, well, that's not what doing it for just one flow or one with everything fixed isn't interesting. What happens is these change. So they don't just go like 1, 2, 3, 4, 5 for the Reynolds number. They do powers of 10. 10, 100, 1,000, big changes. and make these numbers really, really big. And see how changing just one thing affects the entire, how the system plays out. They run the system that way. And then they'll do the same thing with voids and stuff like that. They'll have fix one of them, alter the other, and they play around with it like and stuff like that. That's graduate stuff in mathematics, or at least fluid dynamics, one branch of mathematics. It's very, like, I did it with astrophysics, so there was more to it. There was the magnetics, because the sun is magnetic, has magnetic properties. It gets pretty crazy. Like we were using Fortran 90, and my code would run for 8 hours on a supercomputer. A supercomputer, not my laptop, on a supercomputer. When I tried to let it run, like when I was letting it run on my laptop, I just have to let my laptop run for a couple days just to get an answer. Supercomputer speeds up how quickly you can do it, because you're not just looking at one square, you're discretizing an entire domain, turning it into a giant giant 3D matrix. MATLAB is a great MATLAB use. I bet it probably code up better in MATLAB than what we were using in Fortran 90. But I'm not certain. That's it. That's all the exciting stuff. I hope you guys did well on your physics.
Nah.
This is just a little sample of shit that what you can see in higher order stuff. It's not complete by any sense of the thing. It's just a sampling of it. Fluid dynamics is a very interesting topic because it does study shit like the sun. It studies stuff like flight. There are so many different branches of fluid dynamics. Aerodynamics is a study of fluid dynamics. So like NASA, that's how I was working at Ames. I was in the aerodynamics branch, which is the wind tunnel and stuff like that. So just like they had that, I was showing that little like fish tank with dye going down it. They did the same thing in the giant wind tunnel at NASA. Let's just bring that up. See if I can find a picture of it. I want to say it's 80 feet by 120 feet. I don't see the wind tunnel there. It's way up there. That is not a good picture of it. That's the side profile of the wind tunnel. It's got a giant, this is the one side of it. It's got a giant outlet. There are fans in there, fans the size of cars, bigger than cars, so that they're all along one wall. They're churning, they pump that son bitch up super fast so that the wind flowing down the tunnel is all uniform. And then rather than using dye, they use smoke. They have tiny little metal pieces that stick up and emit smoke, and they test things like that. And then they can open, you can't see it here, a little further to the right in this picture. It's got like the side of the wall opens up, and they can pick up like a Boeing 747 or any type of aircraft and put it in the wind tunnel, and then test the conditions. They have vents at the other end, so they can angle the vents. Let's see, they can angle the vents, stuff like that, so they can like change the way the wind's flowing and see how it affects the impact on the things that are flying. So there's a lot of neat stuff in aerodynamics, which is a branch of fluid dynamics. So lots of fun stuff. If I can get the tour going, I'm sure you'll be going in there. It's one of the biggest in the world. All right. I hope you guys have a great winter break. Any questions?
We're good. Thank you.
You're welcome. I'll be around next semester.
day
I'll
4?
try to do the study group. I don't know. I'll work with you guys over Discord or what day we'll do it. I'm gonna be sitting
Okay.
in on circuit analysis. If anyone else is taking that, I'm gonna sit in on it and take the lectures. I won't be there for the labs, but I'll be there for the lectures. I had an interest in this before, and now that I'm a teacher, I've got some free time to do it. So I might be taking classes with you guys. How about that?
All right.
That's it. Have a great winter.
All right. Thank you.
Oh
Uh-huh.
yeah,
Thank you. You too
I
as
was
well.
actually. Yeah, I was actually considering next semester, since I'm assigned for another Calc3 class, I was thinking about having the students from there. I was going to provide the Discord link for this Discord for it, so they can get out another outside source just in case like they can't reach me or Mrs.
Ah,
Harper.
yeah. It's a good idea.
Yeah.
And definitely show them my YouTube videos. Show them where to find it.
Oh yeah, I'll definitely do that. That's definitely a good idea. All right,
All right. Have a good one.
you too.